We are live and in action here. I'm going to reshare. I'm going to restart the presentation. And here we go to the races. All right, are we back live? Everything's coming up. You'll also see that I have the transcription going on at the bottom of the PowerPoint. That sometimes can help during these presentations if the volume is low or otherwise I'm not being clear. It seems that the PowerPoint transcriber does a pretty good job these days, like intelligently trying to transcribe what I say, which is amazing for me because I'm from Southeast Kentucky originally, and I'd like to think that I don't have an accent, but there are days where I know that I get the people looking at me like the old RCA dog with its head turned off to the side. And whether that's because the words that I'm using or the way that I'm saying them, I just kind of take a break and start again. So, all right. Thank you very much. My name is again Lee Floria. I'm with the Washington Geological Survey. I'm the program manager for the Earth Resource Program. We do hydrogeology, geothermal work, and carbon sequestration in the state of Washington. We have several ongoing projects. You'll see how some of that relates to what I'm going to speak about with regards to Mount St. Helens. I'll try to make some of those linkages to that work, but then I'll also make a whole bunch of linkages to the work that I do for fun, which is what you see on the title here, which is Caving from Fire, because most of my cave research and cave work has been done in places like Kentucky and Florida, the Bahamas and Romania, in good old-fashioned limestone, which is not a super duper common thing in the Pacific Northwest, except in some pockets. So when you do find caves, they're most commonly going to be in basalt and associated with our big volcanoes throughout the region. So you'll also see a couple of names here, Christian Stender and Linda Sobolewski. Christian Stender is with the Alberta Speleological Society in Calgary. He has been very active in this work, doing a lot of the mapping and exploration. And then Linda is now a postdoc in Iceland and just finished her PhD in Germany. Some of the data that I'll present to you is from her PhD dissertation work that was done at Mount St. Helens. There are some other people that will come up, and I'll mention their names along the way because it is a whole group of people of which I'm just one little domino of this whole big field of researchers that's put a lot of work in on these mountains, not just at St. Helens, over more than the past decade. So thank you very much, and we'll get started. Maybe. There we go. Okay, so again, taking a big view, far view back, like this is the karst map of the United States, places where we find limestone and caves and some things that like have been a big part of my life since the early 90s. Up in the upper right-hand corner is where we're at, which is the Columbia River Basin. If you look at the U.S. karst map, there's not a whole heck of a lot there in terms of classic cave and karst environments. A lot of that has to do with the underlying geology. This is a very complex geology, and you'll see some of the bullet points pop up in the left-hand side that contribute to how complex that geology is. We have no time to go through this whole list of items, but the Washington Geological Survey is involved in a great deal of this work over the past several decades, doing fundamental geologic mapping and data collection throughout the region. But broadly, what you have is you have a old continental margin that was passive that transitioned into what we see today over the past 50 to 60 million years. And as each little piece of the puzzle got put together and accreted onto the western coast of the United States, we started developing the complex landscape and geology that you see. Let's see, admitting. Oh, great. There we go. People are in. All right. So let me show you a couple of Things that I mean here. All right, we're going to go through again. This is the Pacific Northwest. You'll see a couple of the most important aspects that I feel help contribute to the geology in the region. That is, one is the Columbia River basalts, which are there underneath your feet in Portland also, but extend all the way over into western Idaho and down into southern Oregon. They date from about 17 to 15 million years. They're exceptionally complex in terms of how they formed and the number of flows and just the sheer volume of lava that was extruded during that time period. And it's a big part of what my team does at the Washington Geological Survey. The other aspect of this is the Yellowstone hotspot, which you can see the track of that over the past, again, roughly 17 million years. And so what I'm going to overlay on this are some of the important key things that have happened. The blue line is not quite exact, but approximately the boundary between the old North American continent, the craton, the crystalline basement rock, and then the rocks that were accreted to the West Coast over the past, 50 to 60 million years. And as pieces of that happened, we see like new geology being brought to North America. And then, of course, as I mentioned, the Yellowstone hotspot has moved through this region through time. And when I say move through, it's not done the moving. North America has the one that moved over the top of it, right? And so as the continent moved over the hotspot, the relative position of the magma rising changed. And you can see the dates of each of the older calderas and notice that sort of parabolic shape that kind of extends around the Yellowstone hotspot with all those black dots. Those black dots are earthquakes. And then you can see that they're organized along with the mountain range around it, what looks like the wake of a boat passing through the continent. And I think that's absolutely fascinating that the movement of a hotspot over 17 million years that you see mimics what you would see as waves moving away from a ship as it moves through the ocean. What was not known until more recently is that there are other parts of that hotspot that are recorded elsewhere. The first one I'm showing you is in north and east of Redmond, and that's where Smith Rock State Park is at. And that is another piece of one of these old calderas that used to be where you see the arrow originating and has moved to the north. And then another one is the Olympic Mountains. So those date to about 55 million years. It is a exotic terrain that is called Zaletzia. And as that formed, think of it like the Hawaiian Islands. As those islands formed as a big volcanic basalt complex, they were shifted to the north and then they were pushed east and slammed against northern Washington to create the Olympic Mountains that we see today. So the crescent basalt that you see around the east side of the Olympic Mountains, and then of course the Black Hills near Olympia, that's all also crescent basalt, the Doty Hills, and then there's aspects of so the Willapa Hills that include that too. So what has happened is you see a northward shift that's related to the relative motion of the Pacific crust to the North American crust. We see that down in the San Andreas fault system. And then as that's moved north and this Juan de Fuca plate has subducted underneath North America, creating the Cascade Range, that relative movement of the Cascade Mountain creation towards the east and the relaxation of the crust in the Great Basin towards the west has created a relative clockwise rotation of the crust in the Pacific Northwest, such that if you look at GPS tracks of the Earth's crust as measured using GPS stations on the Earth, you can see them rotating around what's called a Euler pole in northeast Oregon, roughly around where the Blue Mountains are at. And so this rotation of the crust, that clockwise rotation, is creating the Great Basin, the Cascade Mountains, but it's also creating the Yakima Fold and Thrust Belt. And it's also relating to the volcanism that we see. So that just sort of gives you an overview of sort of this like big overarching picture of what's happening in the Pacific Northwest. But of course, the main focus of what we're here to talk about is the fascinating volcanoes and the aspects of those that are like pretty darn cool for what I do with cave and karst research. So here are the five big ones sort of in and around the region that you can see from this aerial photo from Mount Jefferson. I'm using the traditional names on the screen. So Mount Jefferson in the south, and then Mount Rainier on the furthest horizon on the north. And so Lewitt or Mount St. Helens is there on the west-hand side. But a great deal of work that I also do is over in Klickitat, which is Mount Adams near the cities, the little communities of Trout Lake and Golden Dale, dealing with the Columbia River basalts and thermal springs in and around that region. Okay, so here's what drew me to that area. And over the past decade, we have finally gotten around to publishing some cool papers on the work that we've done. Most of these that you see cited here are free, where you don't have to pay to read them. If you send me, email or a message, I can send you the paper if you can't access them. They are clearly, scientific papers, so there's a lot of like fancy smashing language in there, but we try to make it accessible, and with some cool photos and cool descriptions and cool images. And I'll highlight some of those in that talk today. So this began for me in 2015, but it was far from the beginning of this work. And what I have sort of learned over the past decade of this work is that it's changed how I think of karst. Karst is a Slavic word, or a Slavic a word that comes from Slavic and then was Germanicized from kras, which means barren and stony ground. And it helped describe the landscape in Slovenia, but it has been applied as a term related to all landscapes that have developing caves, primarily in limestone, but also in gypsum and in salt and other very soluble rocks. Well, basalt is not soluble in that way, but we still have lots of caves. Ice is clearly, it's not soluble so much as it melts, but we clearly have caves in ice. And so the broader definition of karst, as I'm trying to think about this, is your moving mass within something called the critical zone. The critical zone is everything from the tops of the trees to the base of active groundwater flow. It's where all of your biogeochemical cycles happen that deal with like Earth surface and what happens at the Earth surface in terms of life and climate and all of those things. And so what we're moving mass, and it's because we're changing the phase of something, like limestone dissolves into calcium and carbonate. Ice dissolves into water, rock melts into lava, right? And so you're changing the phase from solid to liquid or solid to gas. And then you also have to have something that drives this. And so they're gradients. They can be hydraulic gradients, the movement of water. It can be biogeochemical gradients dealing with microbes or just chemical gradients. And it can be thermal gradients, which of course in volcanism is a very important aspect and a big part of what I've been looking at in the past 10 years. So let's start with work that I was not involved with. This is nearby to you. It's Mount Hood. This is the west face of Mount Hood, and this is the Snow Dragon cave system that you see with the red outline. This was mapped by members of the Glacier Cave Explorers, which are based in Redmond, Oregon, at the Oregon High Desert Grotto. And what's really unique about this cave system is that it's not like the ones I'm going to show you images of here in a bit. In fact, it has flowing water in it because it originated as an interglacial stream, so a stream beneath a glacier that was thermal. And because it had thermal characteristics to it, it enlarged the cave much larger than you might find in other glacial systems. But because of retreating glacial mass, the Sandy Glacier has retreated quite a bit up the mountain since they started exploring. And because of the heat transfer melting the ice from below, most of this cave system has disappeared since they first started exploring it in around 2010 to 2011. So that cave is mostly gone. But there was some great research done on that cave looking at climatology and water and heat transfer and how that contributes to its formation. So then where I got involved was in 2015 at Mount Rainier. And of course, Mount Rainier has long known there were caves on the Paradise Glacier near in the Paradise Glacier near the visitor, not quite at the visitor center, but upslope from the visitor center, and then in the summit. And over the courses of a few years, with a fairly large team, we mapped the longest and highest what we call glacial volcanic cave in the world. And I think I can show that in the next couple of slides. I don't need to elaborate here because the next few slides do a better job of it. So, okay, we did 3 expeditions. I should say I did 3 expeditions. There was one before I got involved that was more of a reconnaissance mission. These are, as you might expect, pretty intense operations, not just because it takes a lot to get up there, but it takes a lot to get everything else we need up there too. As you see here, this is Tabby Cavendish. She's carrying roughly 80 pounds of gear, including a nice, beaker flask on the side for doing density measurements of ice. In the cave. So we're carrying huge amounts of gear up there, and these operations took, upwards of 100 people to help porter equipment and scientific and logistical supplies up there to basically live on the summit for a week. These caves had been known from all the way back in the late 1800s, and the first real expeditions happened in the 1970s. They were revisited in the 80s, again in the 90s, and then our group in the 2000s. What that means, what is really cool about this, it gives a longitudinal study of sort of how those caves have changed through time. And because of this, we have a pretty good sense of like why it looks the way it does, and how that has evolved. So I have a little video that shows you sort of what that cave looks like in the summit, and I think it's just fascinating. It looks like basically an ice cream cone. It just kind of sits right there in the east crater of Mount Rainier, and the lower contact is the crater wall, and the upper contact is basically the glacial plug. It's about 3.5 kilometers long. It's about 500 feet deep, which is pretty awesome. And more than that, it's just astoundingly beautiful. So this is the sort of main passage that wraps around the inside of the crater, and you'll see its dimensions are rather large, upwards of 30 meters or about 100 feet in height and width in some places. And it's just amazing that like you get something like that. You'll also see steam rising, and that's because there are fumaroles, and it's the fumaroles of heat that are helping to melt this out. So we have our glacial plug. That glacial plug is being heated by fumaroles and just convection and conduction of heat from the rock beneath. That's melting that ice. That water then is accumulating in below the ice plug, and then advection of air from one entrance to the other is moving some of that steam and air through the cave, which maintains its shape. And it also causes ablation of the walls, creating these beautiful, huge scallops that you see on the side. Okay, so that is Mount Hood and Mount Rainier. So now let's talk about Mount St. Helens. And, this is, I'm going to show you a few different aspects of work that have been ongoing there. And I'll start with some of the lava tube work on the south hand side, and then I'll progress into the crater, and then I'll take a step back and talk about more of the geothermal type work that I've been doing. So, we can't talk about Mount St. Helens without talking about the fact that it's pretty irritable sometimes and decides to like let us know that it's still around and still active. And we certainly had the 1980 eruption, which was really incredible. I remember being a kid and seeing that on TV and just being astounded by how incredible that was. But I was nowhere near it. But I've heard stories of people, in the region from Portland and Seattle, and over towards Yakima and Ellensburg, who've told me about living there and experiencing that and how just whatever adjective you want to use, like terrifying, beautiful, crazy, scary. Like, I've heard just all kinds of descriptions of what that was like. And, you know, it wasn't the first time. Mount St. Helens has been very active. It is among the more active volcanoes in the Cascade Mountain Range. Certainly in the Holocene, so in the past 10,000 years, we've seen a whole series of eruptive sequences that have happened leading up to the 1980 eruption that have created the shape of the mountain that you see today. But more broadly, the mountain is actually only about 275,000 years old. The Cascade Mountains are quite young. Like when you see the Cascades as they are today, they are highly modified by fire and ice. You create a mountain, you weather that mountain down. And that happens in the geologic blink of an eye. And so Mount St. Helens is no different. The mountain roughly dates to about 275,000 years ago, and it has remade itself several times since then. It has grown, it has broken down, it has grown, it has blown its top. It keeps going through these cycles, and we're only seeing the most recent iteration of what the mountain looks like. But I'll draw your attention to, I want to go back one here to the Smith Creek flows that you see and that cave basalt that you see labeled there. Because that cave basalt has been a focus of a lot of like the Pacific Northwest cave adventures for the past several decades. That cave basalt lies right on top of the Swift Creek fans, which were massive lahar and pyroclastic and avalanche deposits that came down the Proto Mountain down towards Cougar and filled the valleys in eruptions that were larger than the 1980 eruption sequences. And then the basalts that you see today were laid down on top of that. So let's now go to this area and I'll show you a couple of things. First of all, this is from our Washington Geology portal at the Geological Survey. The pinkish color that you see are the basalts. These are all the younger basalts, right? So the Holocene basalts that you see, less than 3,000 years old. This flow, the cave basalt flow, were really in two lobes and two phases that wrapped around Green Mountain, and Green Mountain remains today as a kapuka that kind of stands up and away from the rest of the flow. You can see the flow stand out in the LIDAR data for Washington. And on this, if you look closely, you'll see lots of little squiggly colored lines. All of those squiggly colored lines are caves. They're all lava tubes. There's more than 500 of them on the south flank of Mount St. Helens. And some of them, of course, are super duper well known and popular, like Ape Cave, which is sort of shown here in this bluish color. But there are lots of others that maybe some of you know, maybe some of you have visited, and then lots that most people don't know and have never visited because they're fairly sensitive geologically or have fauna such as bats that the Forest Service tries to protect. And so the cavers have a working arrangement with the national forest to help like explore, protect, monitor, and otherwise keep these places protected for future generations and for nature. And then, of course, for me, I'm going to show you a little bit about the hydrochemistry of the work that we've been doing. And this is again from our geology portal, and all of the little triangles are various springs, from those that are cold springs in yellow to those that are hot springs or fumaroles in sort of deep red. So there have been lots of pieces of this happening over a long time. So obviously the volcanology is exceptionally important to people's understanding of how volcanoes work and natural hazards in the region, but also the natural resources that those lava tubes hold are really important for the national forest and for the broader ecology of the region. Then for me, you have the geothermal work because you have definite heat sources and how those might be utilized for clean energy initiatives. And then NASA has been very interested in understanding lava tubes and glacial caves because those are the more likely scenarios that we'll find throughout the solar system, because not a lot of limestone elsewhere in the solar system, unfortunately. Okay, so I was working, this is last year. This is with Simon Fraser University. This was Sarai Munez. This was her master's thesis using something called GeoSlam. So GeoSlam is a backpack LiDAR unit. It looks like a power drill a cordless power drill that you carry in your hand with a backpack, and you just walk through the cave, and it sends out a spinning 3D laser at about 300,000 points per second that it's collecting. And as you walk through there, it's basically recording the distance to its wall, and it's recording where it's at so you can piece it together into a 3D map of the cave. So this is the inside of Ape Cave in the upper left. And that is done with GeoSlam. That's been downsampled to like 1/10 the resolution. In the high resolution versions of it, you can actually see the brass placards and read the numbers on them from the old survey stations that were put in there. On the right-hand side, this is photogrammetry, so taking hundreds of photos and stitching them together in a 3D way so that you can basically create a pseudo 3D image, and you can use those two and wrap them together to get a real good idea of what the shape and morphology of Ape Cave looks like in a way that was never possible before. What she was doing this for was funding from the Canadian Space Agency to look at ways to use remote sensing data to detect lava tubes on places like the Moon and Mars. So yes, using a LiDAR is awesome to map the inside, but what if you're using a satellite above the surface and sending a beam down to the surface or remotely collected data? How would you know that it's there? Well, she was looking at microgravity. When you have more material, you have more gravity. When you have less material, you have less gravity. And obviously a big hole in the ground, a cave, reduces the amount of rock and should theoretically slightly reduce the amount of gravity where you're measuring over top of the cave. And so she took the LiDAR data, measured the morphology of the cave, did a prediction on what the gravity should look like based upon the shape of the cave at that place, and then went out with a microgravity meter to measure what the gravity was indeed, to do a comparison between remote data and actual model data, so that you could take this kind of proxy and put it onto a lunar mission, so where a rover could like collect gravity data moving across the surface and see if they could detect signatures of what might be lava tubes beneath the surface, because those might be places where you might have better chances of establishing habitation areas from protection from cosmic rays and from temperature extremes, and be able to set up an atmospheric chamber, right? So that's, the idea behind that. I think it's awesome work. But there is a lot more to what's going on Mount St. Helens than just the lava tubes. A lot of the work that I've been involved in, and that I mentioned along the way, was the glacial-volcanic caves. And so those also have planetary mission implications for places such as Europa and Enceladus. And then from a perspective here on Earth, climatology is really important, understanding how the evolution of these is tied to changing climate. The geochemistry of these is awesome because you're trying to understand how the volcano and the fumaroles are interacting with the ice, and if you can see signatures of changes that might relate to changing volcanic activity. And then, of course, the geomorphology kind of ties those pieces together because you're trying to understand how these grow and how they evolve through time based upon all of the variables that are, external and internal to them. So back in roughly 2011, they on a helicopter mission flying over the top of Crater Glacier, they saw a big hole, and they called that hole the Godzilla hole. And so you can see on the right-hand side a couple of team members. This, I don't know, I don't think I have a date on this photo, but this is the Godzilla hole, and they're rappelling down into it to see what's there. This was the first attempt in Mount St. Helens to see like what might lie underneath. That cave has since sealed up. I mean, it looks huge there, right? But there's no way into that now. Like, it is filled in with ice. These are very evolving type systems. And a big reason is that Crater Glacier, unlike most other glaciers, certainly in the Pacific Northwest, but really in the world, is expanding rather than contracting. And so on the left-hand side of the screen is a time-lapse LiDAR from 2009 to 2017. So we're looking at roughly 8 years of time between one LiDAR data set and another LiDAR data set. And you take the two, you line them up as perfect as you can, and you look at the differences between the elevation of the Earth between those two times. And where you see blue, there is a lot more change in elevation. Where you see red, there is a lot more reduction in elevation. And so obviously the take-home message, which everybody kinds of knows, that knows things about the glacier on Mount St. Helens, is that it's growing. It's not only growing in its upper part, accumulating more ice, but it's flowing down and kind of extruding out like toothpaste into the breach and towards the pumice plain. And so you can see the toe of the glacier has also been increasing. Because it's so dynamic and because it's growing, it's a great laboratory for understanding how those caves have changed through time. Now, as we're exploring these caves, one of the most important things that we have to deal with is our personal safety. And so all of our missions include respirators. You'll see here two, I think it's Eddie and it's Tom that are here, and they are wearing respirators. Now, interestingly, on Mount St. Helens, they're pretty free of gas compared to some other locations, but we still have them in case. And then we also carry gas monitors that are constantly recording. And so if we have like a burp of volcanic gas and it picks that up, that we know, we hit our safety marks, and then we either need to get out of there or put our respirators on or do something else. But we haven't really encountered that on Mount St. Helens. Now, what's really, really cool is on Mount Rainier, we've seen that. We've seen where those volcanic gases accumulate. Because they tend to be more dense than air, they sink to the bottom. And so this is from West Crater and Mount Rainier, and you can see where it's labeled CO2 trap. And so that carbon dioxide sinks and it accumulates. Because you can't see it, that makes it more dangerous. It's just gas. But if you like, there's locations where if you dip your head below a certain level, 2 breaths and you'll pass out. That's how high the concentration is. And this is a story I always tell. It's amazing that the density contrast between that, we have had like where you're doing a laser beam to like make measurements for surveying, and the laser beam goes through that boundary from the atmospheric air to the carbon dioxide, and it refracts off of that like a straw going into a cup of water because of um, the density differences between those two. So I think it's just amazing that you see that. But again, on Mount St. Helens, we're pretty free of that. So these are photos. I think a couple of them are from Rainier. The middle one there, I believe that's from Mount St. Helens. There are different types of passages that we find. Obviously, on the left-hand side, you have a fumarole-rich passage near the edge of the crater, and you've got steam that's melting it out and conducting that air to the outside. On the right-hand side, you have this big meandering, long, big passage that's kept open by the fumaroles. But more often than not, you have a lot of those middle passages, which are basically where there's just enough heat to kind of melt out the ice that's there. And as we've collected data, so this is roughly 3.5 kilometers again of various caves on Mount St. Helens that have been mapped. They kind of run around the edge of the lava dome. You'll see the colors, those colors, which I don't think there's a code on here, but those colors are coded to the year of the survey. And so there are some caves, like you see Mothra Cave, they're all named after the Godzilla pantheon. So Mothra Cave there in the middle, you'll see multiple surveys of it, and you'll see that it looks different each time. And the question, scientific question, is why does it look different each time? Some of that is because as you see the glacier advancing and sort of ramping up onto the lava dome, you're creating more areas where you can have melt. But also you have changing dynamics of the amount of heat that's coming out of the volcano. So let's take a look now at some pieces of what Linda's dissertation work was. So she flew drones over, oops, I went a little too fast there. She flew drones over the volcano crater, looking at the lava dome and the cave entrance, doing LiDAR work, but also photogrammetry work and temperature collection work. She also collected carbon dioxide concentrations in the soil and temperature in the soil across the lava dome and around the cave entrances. And she had data loggers measuring the temperature for several years inside and just outside the caves. And so let's see what the picture that comes out of that is. So here we have some of the photogrammetry work showing the cave entrances on the edge of the lava dome. You'll see the sniff monitoring station where the USGS is collecting carbon dioxide and sulfur dioxide concentrations. And then if we bring up some more data, here is Mothra Cave, 2 different surveys, 2022 versus 2023. You'll see that they changed immensely between those 2 years. And in particular, Mothra Cave was incredibly smaller in 2023 versus 2022. So why did that happen? Why were they growing and then all of a sudden stopped growing and got incredibly smaller? Okay, leading question, because obviously I'm going to show you some data now to help maybe explain it, but it's still in the realm of hypothesis. We don't have like full understanding of the true link. But in the southern Washington, you have a fairly large geothermal area. This is the Columbia River on the bottom, where you see brighter colors. That's where you have more favorable geothermal heat that has been measured. You see hot springs and cold springs. You also see faults and stuff located on there. Mount St. Helens and Mount Adams are both visible. You'll see them as hotter spots. Mount St. Helens is kind of off by itself towards the west. Part of that is the reason it looks like a hot blob in the middle of nowhere is because there's much more rain on the west-hand side, which suppresses the heat. Okay, so these are the areas that we're principally looking at for geothermal like heat and trying to understand the why of those. Don't need to go into that all today. All right, now here's going to be the data. You don't need to understand all this. I'll lead you through it the best I possibly can. This is what's called a Durov plot. This takes your positively charged cations on the left-hand side and your negatively charged anions on the top side, triangle, and it takes those two triangles and then it puts the data in the middle in the square so that you can see what a pattern is. The cations, that's calcium, magnesium, calcium, sulfate, sodium. The anions, chloride, sulfate, bicarbonate, and carbonate, right? So what you'll see is symbols that correlate to like older data, newer data, and the location of where those data come from, whether that's the fumaroles, hot springs, pumice plain, or the cold springs that surround Mount St. Helens. You'll also see the total dissolved solids, so the amount of stuff dissolved in the water, and the pH. So we see a line at a diagonal in the middle, and we see kind of a pattern that's more that line going down. That first line is related to what we call simple dissolution or mixing. So there's things that are happening with respect to like the volcanic heat that are dissolving minerals and mobilizing minerals. Then we see this line here, which is related to what's called cation exchange. So that's basically you have like cold water moving through a rock and it'll substitute a calcium for a magnesium or something, right? Which happens, it's a slower process than dissolution or mixing. And you can see that those are the two principal patterns that we see for the chemistry. But when we take that through time and temperature, we see that we have patterns in both of those in time where the sulfate is decreasing through time and the chloride is decreasing through time. And there's a similar correlation that as you have colder temperatures, you have less sulfate and less chloride. That is fairly normal in a volcanic system. When you see higher levels of sulfur and higher levels of chlorine, you have higher contributions of volcanic gas. And so as we move further and further away from the the eruption phases, we see less heat and we see less of those volatile chemicals that are exhaling off the magma. So not a big surprise there. As it gets colder, you have less activity, you have less of those gases. Okay, well, so what I think we have is a dynamic equilibrium, where if you look at satellite data of temperature and you take a look at how that temperature inside the crater has changed, you can see since the last eruptive period in 2004 through 2008, the temperature has gradually decreased at the surface inside the crater on the lava dome. That's expected. We also see from Linda's data over the past several years that the heat, the temperature of the fumaroles has decreased. So it seems like there's less heat output as we are moving forward in time, which makes sense. We've moved further away from the eruptive cycles. And so one might imagine that if you're trying to take all of the different pieces of the puzzle and put them together, that of course, as you have heat flux from the eruption, you're going to melt ice. And then as that eruption ends and starts cooling down, you create a lava dome, which is there, which seals that off and plugs it up. Then you start accumulating more ice. And as you accumulate that ice, you're going to create voids in that where it's touching the hot rock and where you're getting fumaroles coming out. And you get caves forming. But there's sort of an equilibrium point where you're no longer able to create as much cave because the temperature's decreasing and you're getting more ice. And so I feel like we might be, this is hypothetical, that we might be at a point where we've kind of crossed over sort of that maximum amount of cave development, and we're starting to see them trail back off as it's getting colder. So that's kind of the big picture. I don't have really a lot to say. That I work in Illustrator, so this is one of my Illustrator drawings just for funsies, but it shows you sort of the full system. If you do a cross section from south to north across St. Helens, the various types of springs, hot, medium, and cold, and the contributing sources of heat. But the main points here is that we're in a very young and complicated area in terms of its geology and landscape evolution. The volcanism has basalt phases. Those basalt phases have lava tubes. We have, as I say, ridiculous amount of trees and precipitation. And because you have a ridiculous amount of precipitation in some areas, you have glaciation in higher elevations. That where you put that ice on top of the hot rock, you get glaciovolcanic caves. When you move the magma around, you're creating heat flux and you get geothermal activity, and that the formation or speleogenesis of these caves and the evolution of the landscape happen at a much faster rate than you might find in areas sort of in the middle of the continent where you have less of these things happening. Just as a counterexample, the caves in Kentucky and Indiana and Tennessee, where I do a lot of my work, the older passages there might be 6 million years old. The upper levels of Mammoth Cave might be upwards of 6 million years old. Whereas there in the cave basalt, those caves they were formed 3,000 years ago. That's it. Boom, done. And I think that's an incredible difference between how you see and picture these landscapes. Last note, and this might be something I'll talk to you all about later, is we did a reconnaissance trip at Mount Baker back in the beginning of September, because on the Sherman Crater on Mount Baker, guess what? There's a glacial plug and there's tons of volcanic output. Huge amount of heat flux. That heat flux has translated into glacial volcanic caves. So we were just there. We mapped some of the volcanic caves and we were making plans for a big expedition next year in 2025 to go back there with a large team to actually properly document what we see, to collect specimens for microbial work, for NASA type projects, and for the USGS for volcanic projects. So we're going to be working on funding models and our team composition and trying to get the logistics for the permitting worked out through the Forest Service here over the next couple of months. We're going to call it the Morgoth entrance, or the Morgoth system, referring to Lord of the Rings, if you're into that legendarium, with all the various acolytes of Morgoth shown there. And it's a pretty incredible place. So anyways, thank you for your time. Appreciate it very much. And I'm happy to answer any questions that you might have.
Oh, there you go. Now I'll get other stuff.
All right, I'm going to stop my share.
Well, he falls asleep.
I like you. I like you.
Okay. All right, thank you, everybody. Happy to take any questions that you might have. And if not, I'm always happy.
Hey, Lee.
Yeah.
Lee, This is Drew from the caving. So, what kind of interactions, if any, do you have between some of the glacial caves and lava tubes? Do they ever get close to each other, or you're muted still?
Very much. That's not something I've seen, but that's a really cool idea. um, Trying to think of, I I think that in the Cascade Range, my guess is that you might not see it just because of how and where the basalt flows extrude. They tend to be at lower elevation rather than at higher elevation. So, your glacial masses might not get kind of come down that far, and the basalt might not go up that high. I know that there are clearly, and I know you know this too, there are caves that have ice in them. Lots of those over around Trout Lake and places because of just the, how cold it gets in the winter and the amount of snow. But that's a different thing than what you're talking about. And I haven't seen that, but that would be really awesome if that happened.
Yeah, no, but I mean, it makes sense based on the elevations. Okay, cool. Thanks.
Yep. Mm-hmm. Great. Other questions?
Question about where the funding comes from for these expeditions.
Yeah, well, obviously, which I kind of that last slide I kind of blew through a little bit, had a whole list of different contributors and partners. For the Rainier work, we had National Geographic. I think Mazamas helped. Forget which of those three expeditions that there was a grant from Mazamas that helped fund that. Petzel gave a fairly large contribution when that was mostly like in-kind contribution for equipment, whether that was pro deal or otherwise. There were lots of other sponsors, anything from like Pro Bars to Justin's, all those various like things. They go a long way when there's a dozen people living for a week on the summit. But in terms of the sheer funding, it's cobbled together. We've never had like the big grant to do it. The closest that came was when NASA was working like at Mount Meager and the Athabasca Glacier with the ice effector screw for their missions. But that's not like funding they gave us. They basically funded the mission to do those. But that was not at Rainier or St. Helens. But those are models that we look to. Right.
I've got a question. I have become aware recently of a lot of lava tubes, obviously in the Gifford Pinchot, near, like you're saying, Trout Lake, Adams, and St.
Yeah.
Helens, but don't really know of any in the Hood area or like Rainier area.
Yeah.
Are they up there too? Are they very common there?
And I think the answer is largely no, and that's because of the style of volcanism, right? To get a lava tube, you have to have a very low viscosity magma, right? So as opposed to like an andesite or a dacite, you need to have a basalt. And that's just because an andesite or dacite does not flow that fast. And so you can't get the flowing magma that creates the lava tube if it's really sticky, and so that you need to have the basalt. And so like at Rainier, I mean, you can get basaltic intrusions and extrusions, but not lava flows in the same way. Baker similarly doesn't have that much. Hood, I don't think has a lot. I think there's some around there, but not on the mountain that I've seen itself. But clearly, when you go further south to like the Sisters, to Newberry, to Klamath, you have a large number of lava tubes sort of on the Oregon high desert side from the lava flows coming off of those volcanic complexes.
Right, gotcha. That makes sense.
Mm-hmm.
Thank you. While I'm talking, are there many? I've been blown away at just how many caves there are. I never really knew about them until recently. But are there
Yeah.
many, you think, that don't have any entrances at all and are just
Oh,
huge chambers
boy.
underground that
Yeah.
don't have an entrance? And if there are, do we have any way of finding them? Like, does ground penetrating remote sensing work for things like that?
So I will not defer your question, but I will say this up front, and then I'll give you a bit of an answer, is that there's really some good resources for that. And if you send me a message, I can send you some links to some like various geophysical techniques that are used for that. That's something that I've done in my work. Ground penetrating radar, absolutely. Electrical resistivity, electromagnetics, these are all different types of methods that you could use. Gravity, as I mentioned, is in that too. But to the question is there a lot that don't? Yeah, absolutely. There was a great study by Rain Curl, who passed away a few years ago, unfortunately. He did back in the 1960s, before fractals were a thing. Like, you know, if you like ever studied like fractals and chaos theory, like Mandelbrot had like the big work that he did. But before that, Rain Curl, who worked for 3M, no, sorry, not 3M. He worked for DuPont, I think, chemical. He was a very savvy chemist and mathematician, and he developed like this formula for entranceless caves. And basically what he said is like he took all kinds of databases and he said this many caves have this many entrances, this many caves have this many entrances, and he plotted graphs of those in regions, and he sort of extrapolated like if 5 caves have 50 entrances and 5,000 caves have one entrance, how many caves we might expect that don't have any entrances, right? And so it's like what he called entranceless caves as a measure of karst. And like it was this really savvy mathematical formula that he developed that is based upon natural fractals. Like the smaller things are, the more of them that you have, right? And it's just a neat way to think about it. So the answer to your question is, yeah, absolutely. Which is why a lot of cavers go out and they sniff around on the hillsides and take a stick and poke it in a little hole, feel to see if there's air coming out of it, and then maybe, you know, if you have permission and it's the right place to move a couple of rocks to see if there's something in there. That's how a lot of caves are found.
Okay, cool. Thank you so much.
Mhm. All right. I don't want to keep you all too terribly late. It's later on my end than your end, but I appreciate very much the invitation to present to you all and your attention. I'm going to stop the recording. Stop the recording. There we go.